Welcome to the Dev Journal. I am Sloan. We are seeing a massive shift in how we build today. It is no longer about throwing more hardware at a problem. Instead, engineers are winning through surgical precision, slashing latency by orders of magnitude and clawing back profits from expensive cloud providers who hide behind complex fees. Today, we explore how researchers at Google Artificial Intelligence achieved a staggering 948 times speedup in generative retrieval. We will also analyze Alibaba's new open-source workstation, designed specifically for autonomous agent workflows. These breakthroughs represent a move toward efficiency over raw power, proving that smart architecture beats a massive budget every time. Beyond the performance gains, we are dissecting a massive study of 44 different cloud providers to see who is actually gouging you on data egress fees. Plus, we examine how developers reverse-engineered Amazon's pricing algorithms with 83% accuracy. It raises the question of whether our margins are ever truly safe from the giants.
That is the question I am digging into today. It comes down to whether you can see the patterns or if you are just paying for noise. We are starting with a deep dive into that performance leap in constrained decoding that is changing the speed of thought. I am Vance, and this is the Dev Journal.
YouTube is finally solving the freshness problem in a way that users actually feel. By deploying this static framework, they saw a 5.1% jump in views for fresh videos. It turns out that when the recommendation engine can actually keep up with the clock, people stick around much longer than before. What really strikes me is the sheer scale they are managing without breaking the bank. They are fitting a vocabulary of 20 million different items into just 1.5 gigabytes of high bandwidth memory. That is a massive amount of data to keep reachable, yet it fits perfectly within a commercially viable footprint for production. This efficiency allows them to maintain 100% compliance for freshness constraints, ensuring that the artificial intelligence never suggests a stale video. It transforms a complex technical hurdle into a seamless human experience where the content feels alive. Vance, how are they actually pulling off this level of speed without hitting a massive hardware wall?
They are doing it by completely rethinking the data structure, moving away from slow prefix trees. By flattening those trees into compressed sparse row matrices, the team eliminated the bottleneck where the system had to wait on central processing unit offloading. This architectural shift is what enables that staggering 948 times speedup during decoding. When you look at the performance on the Tensor Processing Unit version 6e hardware, the numbers are even more impressive. The latency overhead is down to 0.033 milliseconds per step. That means the entire constraint logic now only accounts for 0.25% of the total inference time for the model. The secret sauce is the vectorized node transition kernel, which keeps the computation graph static. This move reduces the input-output complexity to a constant big O of 1, which is essentially the holy grail for throughput. It allows the system to handle millions of constraints without the typical performance penalty we see in dynamic searching. It is a masterclass in low-level optimization that proves we have not reached the ceiling of what current hardware can do. By focusing on the math of the matrices, rather than just throwing more clusters at the problem, they have built a retrieval system that is both incredibly lean and remarkably robust for high-volume traffic. We are seeing these low-level inference optimizations pave the way for much more complex systems. As we move from optimizing single model steps to building entire agentic frameworks, efficiency becomes the foundation for everything else. This brings us to a new high-performance workstation from Alibaba, designed specifically to manage those advanced agent workflows.
Alibaba is tackling the biggest frustration with current large language models, which is their inherent lack of memory. By introducing the ReMi module within the CoPaw workstation, they are allowing these systems to retain long-term experience across different user sessions. This effectively transforms a simple chatbot into a persistent and professional personal assistant. When an agent can remember past interactions and preferences, it stops feeling like a temporary tool and starts acting like a true digital colleague. This persistent memory layer ensures that the context of a project is never lost. It is a fundamental shift toward creating artificial intelligence that understands the nuances of ongoing human work cycles. The ability to deploy these agents across every platform we use daily is where the real magic happens. Whether it is DingTalk, Discord, or even iMessage, the all-domain access strategy ensures that the intelligence is present wherever the work is actually being done. It creates a seamless bridge between fragmented communication channels and unified automated logic.
Sloan, if you look at the underlying architecture, the real strength lies in how they have decoupled the agent logic from the actual deployment layer. By using the agent scope middleware, engineers can scale workflows without having to rebuild the entire infrastructure every time a new communication protocol is introduced. It is a very clean separation of concerns. I do have some reservations about how they handle scheduled tasks for autonomous background operations like web scraping or repository monitoring. While the framework provides a stable execution environment through the agent scope runtime, allowing agents to perform these tasks autonomously opens up significant questions regarding security sandboxing and resource management that developers must address. The skill extension model follows the standard set by Anthropic, which allows for immediate deployment of Python-based functions from a custom directory. This makes it incredibly easy to expand the capabilities of an agent on the fly. However, maintaining those functions across a distributed workstation environment requires a level of oversight that many teams might not be prepared for. Despite the potential security hurdles, the way this workstation standardizes interactions across platforms is technically sound. It addresses the statelessness of standard application programming interface calls by maintaining that persistent context through the middleware layer. It is a robust attempt at organizing the chaotic world of autonomous agent development into a single manageable workstation environment.
The stability of these agentic workflows is only as good as the underlying math that powers the code. This move towards sophisticated automation is driving a greater need for rigorous mathematical validation to ensure total reliability. We are shifting from managing agentic logic to cross-validating zero-knowledge systems, moving from Python physics to complex Rust BigInt proofs. The shift towards sophisticated automation is driving a greater need for rigorous mathematical validation to ensure total reliability as we move from managing agentic logic to cross-validating zero-knowledge systems, where the transition from basic Python physics to complex Rust big integer proofs reveals the high stakes of precision. There is a genuine fear that logic drift between different simulation types could lead to catastrophic failures in production zero-knowledge systems, because any minor deviation in Rayleigh-Plesset simulation behavior can ripple through the entire proof and cause the promise of secure and private computation to fall apart completely. Establishing this level of cross-validation is absolutely essential for building long-term trust in systems that manage real-world physics data, because we need an airtight method to ensure that the mathematical representations remain consistent across every stage of the development process, instead of hoping for accuracy in production.
Sloan, the consistency you are looking for depends on bridging the massive gap between numerical Python, float 64 physics, and modular field arithmetic by using a scaled integer bridge, with a scale factor of 10 to the power of 30 to align those 53-bit mantissa floats. The Rust witness generator leverages the number big integer crate to ensure bit-for-bit agreement with the original Python reference model, while using a single simulate inner function to handle both collapse and acoustic presets, which effectively eliminates the risk of logic drift between the two different simulation types. I find it impressive that the compute public inputs function replays simulation steps using modular field arithmetic, because this is the only way to resolve the inherent discrepancies between standard integer division and modular inversion that would otherwise cause intermittent and difficult-to-debug-proof failures in a live system. The engineering team is even performing cross-language trace validation by exporting JavaScript object notation files to verify that the Rust big integer witnesses match the Python references perfectly, which ensures that the finite field constraints of the zero-knowledge environment do not break the underlying physics during the proof.
While we are mastering the art of mathematical proof validation in these niche systems, we are also seeing a shift from the absolute certainty of zero-knowledge proofs toward the predictive power of classical machine learning models, as we analyze how those models are being applied to the complexities of dynamic pricing. The ability for engineers at avlas.com to achieve 83% prediction accuracy for price drops across 50,000 products is a massive win for consumer-facing platforms. This level of precision transforms how we perceive market volatility and gives companies a significant edge in predicting when Amazon will slash prices for specific goods. It is quite telling that this model is already being expanded to other retail giants like Target and Walmart, where it is currently maintaining a prediction accuracy of 76%. Even as the ecosystem grows more complex across different platforms, the fundamental logic of these price fluctuations follows patterns that are remarkably consistent for these major retailers. One of the most fascinating findings from this research was that sentiment analysis from product reviews showed zero correlation with dynamic pricing shifts. It appears that raw numbers and historical trends are the only things that truly matter in this environment, rather than the qualitative feedback provided by customers during their shopping experience. While the business implications are clear, I am curious if the technical architecture behind these 600,000 daily updates is as robust as the results suggest. Vance, I know you have been looking into the specific machine learning models and the database performance that actually powered these high-frequency price predictions across such a massive data set.
The performance gap between different architectures is what really caught my eye because random forest models hit 83%, while long short-term memory networks stalled at just 58%. This proves that deep learning is not always the right tool for tabular time series data, and that simpler ensemble methods can often provide much better results for these problems. On the database side, handling 8,000 inserts per second with 45 millisecond latency using MongoDB time series collections is a solid architectural choice for 600,000 daily updates. They even managed to squeeze out an extra 7% in accuracy by implementing category-specific models for electronics and books rather than relying on a single generic model. However, the data engineering side shows some serious diminishing returns, where a 4 times increase in infrastructure costs for competitor scraping only yielded a marginal 2% improvement in accuracy. It is a stark reminder that throwing more hardware and data at a problem does not always translate to a better outcome when you are already reaching the statistical ceiling. We have to weigh the value of every extra byte of data against the reality of the monthly bill, which is why efficiency matters so much in these large-scale systems. That same scrutiny over overhead is becoming even more critical as we move from the costs of data ingestion to the even more controversial costs of data egress. The true cost of building in the cloud is often hidden in what I call the egress tax, which is essentially a penalty for moving your own data. An audit of 44 different providers reveals a staggering price gap, where costs range from absolutely nothing to $0.55 for every single gigabyte transfer. Amazon Web Services and Google Cloud are still leaning into high-margin rates that sit between $90 and $120 per terabyte. When you compare that to Hetzner, which offers 20 terabytes for free and overages at only $1.18, the legacy providers look incredibly expensive for any high-bandwidth workload. Developer-focused platforms like Netlify and Render are actually the most expensive options right now, charging $550 and $300 per terabyte respectively. It is a massive financial risk for teams because moving a 50-gigabyte model checkpoint could trigger a catastrophic invoice of over $100,000, depending on your infrastructure. This pricing disparity means that infrastructure planning is no longer just about compute power or storage capacity, but about the gravity of the data itself. If you are not careful with where you host your large datasets, the cost of simply accessing your own information can easily exceed the cost of the actual engineering work involved.
Vance, those numbers really highlight how predatory the traditional cloud model has become when compared to the new wave of specialized infrastructure. It is why we are seeing such a massive surge toward providers like Cloudflare R2 and OVH Cloud, which have built their entire value proposition around providing zero-cost egress for critical storage. This shift is especially vital for the survival of artificial intelligence startups that are operating on incredibly tight margins while training massive models. By 2026, half of the major graphics processing unit cloud providers, including RunPod, Lambda, and Vast.ai, have committed to zero egress fees to attract these teams away from the expensive legacy giants. The business world is finally waking up to the fact that these hidden fees are not just a technical detail, but a fundamental threat to project viability. When a simple data transfer can cost 76 times more on one platform than another, the sophisticated move is to decouple your compute from these high-cost data silos entirely. This trend of aggressive cloud cost management is part of a much larger pattern where developers are fleeing expensive ecosystems for leaner alternatives. We are seeing that exact same frustration boiling over in the software as a service world, particularly after the massive price surges we just saw with popular monitoring tools like UptimeRobot.
The monitoring market has been thrown into chaos following the decision by UptimeRobot to implement a staggering 425% price increase. Overnight, monthly rates for their professional tier jumped from $8 to $34, a move that forces development teams to perform a cold calculation about the value of their existing monitoring stack. When moving away from a managed service, you often end up looking at self-hosted solutions like Uptime Kuma, which requires your team to manage their own servers and complex notification integrations. The risk with this approach is the recursive problem of monitoring the monitor, where you need a second system just to ensure your primary alert server is functioning. If your self-hosted instance crashes in the middle of the night, you are effectively flying blind without a significant investment in building a redundant, secondary failover architecture. At a typical engineering salary, spending even 1 hour a month troubleshooting your own monitoring stack costs the company far more than the premium price UptimeRobot is now demanding for their convenience. Development operations engineers must weigh that $34 monthly fee against the technical overhead and potential downtime risks associated with managing these custom setups in-house. While the sticker shock is real, the hidden labor costs of managing a fragmented monitoring environment across different platforms can quickly erode any savings you might see on your monthly credit card statement.
Vance, those technical trade-offs are why we are seeing such a massive migration towards specialized providers who target the middle ground between self-hosting and premium software as a service fees. This price hike is a dangerous gamble with customer loyalty in an ecosystem where switching costs are low for basic website and server heartbeat monitoring services. When a company raises its rates so significantly without new features, it creates a vacuum that nimble competitors like Owlpulse are happy to fill with their $9 flat rates. These alternatives include unlimited monitors and short message service alerts, providing a level of predictability that is essential for startups and smaller development agencies on a budget. Even Statuscake has become a more attractive option by offering specialized page speed monitoring at a $20 legacy price point, proving there is plenty of room for providers who respect their audience. Pulsetic is another strong contender, maintaining a free tier for entry-level requirements while offering multi-region monitoring capabilities that rival the reliability of the most expensive legacy players. That tension between convenience and cost is why precision in both our code and our cloud spending has become the new baseline for success in 2025. Whether you are optimizing your data egress or auditing your monitoring stack, the goal is always the same, which is building resilient systems that do not break the bank.
Reducing latency 948 times using Google's new static approach shows we are moving past throwing hardware at problems. And when you combine that efficiency with the massive price gaps across 44 cloud providers, it is clear that architectural choices now dictate your profit margins more than your actual code.
This shift toward optimization is a survival strategy in a market that no longer rewards digital excess. As we see a fundamental move away from brute force computing toward a future defined by surgical precision, whether you are cutting egress fees or accelerating generative retrieval for your underlying infrastructure. As the industry matures and engineers learn to treat every byte and every dollar with intentionality, we hope today's deep dives help you navigate those difficult choices, while we thank you for listening to the Developer Journal and look forward to seeing you back here for tomorrow's technical update.